Hey everyone, it's Aniruth, and today we're going to be talking about CS61BL, specifically Summer 2021 Midterm 2, Question 7, Part B. Wow, that was a mouthful. Okay, so 7B is a little different than 7A. In 7B, we're implementing a different method called similarity. In this particular case, we're taking some string and we want to find a decimal score that we're going to call similarity. So I'm going to approach this like I was taking it during an exam. What that means is I'm going to have to first figure out what the question is asking. Then I'm going to have to try to think of some ways to do it, and then hopefully implement some solution that fixes it, and then verify that solution by looking at an example or creating one of my own. In this particular case, we're given an example, so that makes it a little easier for us, but let's go ahead and take a look. So in the second paragraph here, we're given what the definition of a similarity score between a key and a word is. It's the length of the longest matching prefix over the length of the key. And then we're given the definition of what this overall similarity is, which is the average of the similarity scores. So there's an example here. We'll come back to it in a bit, but you're more than welcome to take a look. It looks like for bin, belt, and buggy, beanie boy, and chin all have different similarity scores. Specifically, chin, right, has 0 because there's no similarity. Beanie boy would have the entirety of bin in it, so it would have a similarity score of 1, etc. We're also told that we can use any of these methods within TriSet CO61BL, the interface. Hopefully those come into use. And then we're told that we can use these skeletons as a way to get started with this code. So on the left here, I've set up IntelliJ to have these skeletons, and we're actually going to go ahead and implement both of them. But let's take a first look at maybe some strategies that we can use here. So I think the first thing that comes to mind is if we separate these into 2 different tasks. So maybe one way that we could do this is we could have first, we could calculate. So let me write a 1, and then we can calculate the length of the longest matching prefix. And it turns out we can do that because we are given, well, maybe we can use this. We're given longest prefix of. So it returns the longest prefix of the key that exists in the try. Well, is this useful? Maybe, I don't know. So I'll put down that we might need to implement this somehow. And then the second step, after we were to calculate the length of the longest matching prefix, we would divide by the length of the key. And then we would go ahead and repeat for all words in the try set, and then finally we would return the average of all the words. Okay, well, this looks like some pseudocode that would work. And if I was writing my own program, maybe I would just go ahead and do this, but we're under some constraints here. Namely, we need to figure out how to fit this into these skeletons. So it looks like we might be able to do this if we were to calculate the length of the longest matching prefix between, well, actually, I can go ahead and add this between a key and a word. So these both would assume that we have some word from the try, and then we're doing this calculation. So what makes this a little tricky is, well, we don't really have a great way to do 1 or 3. Because the issue with doing 1 is we need to figure out the longest matching prefix between a key and a word, but none of these methods do that. Longest prefix of key that exists in the try gives us 1 thing. For example, in this case, it would give us a beanie boy as the result, right? That's the longest prefix of key, it's the one that has 1. But that's not what we're looking for, because we also are then would be ignoring this 0.5, 0.75, 0.25. And it's not like we can just delete the try or delete it from there, because then, of course, it gets a lot more complicated. We aren't going to be able to fit that into the skeleton code. You're more than welcome to try it out, but it becomes really complicated. And also keep in mind that it's really hard to iterate over all the words in the try set, because there's not really an iterator that we can use. Why is there an iterator? Well, if I look at the interface, we don't have anything that would give us an iterator to iterate over, which means that it's not going to be so easy to repeat for all the words in the try set. So maybe we need to come up with a different way to approach this particular problem. Well, this is looking a little challenging. So maybe what I can do is I can try to look at some of the skeleton code to see what I can figure out. So We could do this recursively using similarity and SimilaritySum. SimilaritySum looks to be a helper method, so probably what we're going to be doing is SimilaritySum here. Look at that, IntelliJ already figured out that's what we want to do. And we'll probably pass in key, and then we'll pass in some index. I don't know exactly what index, and we might do something else afterward. And then this looks to be like a base case, and then we'll probably have another recursive call somewhere to SimilaritySum in one of these two lines. And this looks to be like a for loop where we're going to use index to go through something. I would have thought maybe it was for this, but since we don't really have a clean way to do it, we don't have many lines, it might not be the best option. I'm going to pause here for a moment, and maybe there's a different way that we can break this down. So maybe instead of repeating for all the words in the try set, maybe instead we break it down into looking at the key. And this is going to be a little bit of a hard insight to find, and you might have to try other things. I think a couple other things that are worth trying, or maybe you want to go level by level within the try and check whether or not everything is a key or something like that. But the issue is you don't have the number of lines to do that. So what you have to do is you have to think about what you have here in the interface that could be helpful. So I'm going to go and just write down some methods that might be helpful. Well, to be honest, I can't really think of a use case for clear within this specific method because clearing all items out of the try isn't going to help us find a similarity. Contains could be useful. I don't know where exactly I would use it. Add might be useful. I don't think I need to really add the string key though, because I'm not really comparing. So I'll write down contains as a maybe. I'll put a question mark. Num keys with prefix. Well, we just spent all that time in A. We're probably using it here. So it returns a number of words that start with prefix, but what prefix would we use? We can't just put in the word because then we wouldn't get the 0.5, 0.75, we would not get the decimal values. So maybe we need to think about num keys with prefix. And then we also need to figure out, maybe we could use size. Well, size I think will probably be used, right? Size I can go ahead and mark down as a for sure thing because well, we need size to figure out the number of words because that's how we calculate the aggregate decimal score, it's the average of all the similarity scores. So that seems pretty important. And then we have longest prefix of. Well, longest prefix of, again, I'm not really sure. Maybe we'll use it, maybe we won't. But I'll go ahead and write this over here too. So now we're trying to return the longest prefix of key that exists in the try. We have string longest prefix of, okay. I'm gonna go ahead and remove these. And now we have a couple more options to think about. Well, contains could be useful, but I'm not really sure what I would call contains about because finding the prefixes, well, if I was to find the example of prefix of B, well, it's not in the try set because none of these are just the letter B, but that letter B counts because of buggy. Right, buggy and bin share the same first letter of B. So that's why the similarity score of 0.25. You have one letter, the length of the entire key is 4, so you divide, get 0.25. Here's an interesting thought. And I'll go ahead and write this over here to the side. IntelliJ will probably throw some errors, but that's fine. Let's say I have bin. Let's say I compare by B. Well, belt is going to give me a yes, right? Because we do have B. B is going to give me a yes. Buggy is going to say, yeah, we also have the first letter as being B. I'll go ahead and actually clarify that. Compare by first letter being B. Let's see, Beanie Boy. Well, Beanie Boy is also going to say yes. Chin is going to say no. Okay. Well, if I go another round, let's say I compare by first two letters this time. Being BE. Well, if I go and just copy paste and I sort of evaluate which ones of these are going to be there, I'll do this. Well, belt is going to say yes, B is going to say yes, buggy will now say no, and Beanie Boy will say yes, and Shin will then say no. Let's say I do this again, a total of 4 times, 2 more times. So then I would compare by the first 2 letters, or the first 3 letters being BEE, and then I would compare by the first 4 letters being BEEN for the entire word. So now if I go ahead and take a look, well, belt, of course, is not going to have the entire word. The only one that would have the entire word is Beanie Boy. Belt is not going to have BEE. We have the word BEE here, but I think that this gives us a very good insight as to what we're looking at. Because if we count how far down we go, we can figure out what the score is. So for example, because we made it all the way, this has a score of 1. Beanie Boy, and then, well, B, of course, had a score of 0.75. I'm looking for the final, yes. Belt, well, Belt had a score of 0.5. We already counted for B down here. And then we had Buggy, which had a score of 0.25. And I think this is a pretty big insight, which is that we can break apart how we're looking at this by looking at breaking down the key, because we couldn't break down the triset, right? The original way that I wanted to do this was by iterating through every word in the triset, because we had a nice thing to give us, or not really a nice thing, but maybe there was a way that we could figure out how to get the prefixes. But we couldn't do that. So now I'm thinking about it a little bit differently. Now I'm trying to see if you can go by the letters. And we know how to do this, because it's very easy to break down a key, right? We have a nice substring method that Java gives us to compare for strings. In fact, I'll go ahead and write that down. I'll write down a little bit lower, but I'll say substring. Maybe we can use that to sort of break apart the letters and what these combination of letters are going to be. Well, now the question is, well, what should I exactly do to break it down? Because I think that this, maybe I could do, maybe I can't. Well, actually, let's just go ahead and see how we could do this. I want to go ahead and do the recursive skeleton, because I think that's personally what I would generally start out with, because of the same, we can analyze it by a base case and think about it a little bit differently. So we have public double similarity, we have similarity, we want to call similarity sum. We already talked about that, right? Probably we're going to do that. We have the key, we want to pass the key and index. Well, what should the starter value of index be? Well, there are two values that come to mind, maybe 0, probably. Well, the issue with 0, though, is that if we're using the substring method, well, to get the first letter being B, well, this is going to be substring of 0, 1. That's what we would want to use there, right? Because it's the first one is inclusive and the second one is exclusive. In fact, I think we might have it anywhere. No? Okay. So that means that we're going to, I think at least for this implementation, we could do 1. Maybe I could just add 1 every time to account for the inclusive exclusive. But instead, I'm just going to start with 1. And then since we have a similarity sum, well, a similarity sum is not an average. An average is you divide by the number of words here. So luckily, we have a way to do that. I actually had this written down. We could do size, which I thought might come in hand for this. So I'll go ahead and remove size here, because it looks like we've already used that. Now we have a couple more options here. We have an index that we're using. We have a base case to account for, and then we probably have to do some work over here to figure out what exactly we're doing. So let me start out with the base case. Using this same logic, let's say I go up, well, I want to go up to 4 letters. I don't want to go more than 4 letters, but why don't I want to go more than 4 letters? Well, bin has only 4 letters, right? I can't go like 5, 6 letters if the key itself is only 4 letters. Well, how do I get how many letters are in the key? Well, I can use dot length. So for a string, remember we use dot length as a method, unlike an array where we would use dot length as an attribute. So we have index, and we want to make sure that if index is ever greater than the key dot length, we're going to go ahead and do something. Probably we're going to be returning, what exactly are we going to be returning? Well, we need to return a double. So I'm going to go ahead and return 0, but we can always come back and change it if need be. So now we have this next line over here that we need to fill in with something. Then we have another line over here that we need to probably return something. Maybe we use what's up here, down here, okay? So let's take a look. What I want to do is I wanted to check when we're going to stop seeing it. In other words, I want to compare down here. See how belt is no on line 66? Well, that's because it does not have the first 3 letters, so I know I can account for the first 2 letters. And maybe I can multiply, right? If I account everything as being, well, first let's just take a moment and think about how we got to 0.25. Well, we got to 0.25 because we're comparing by the first letter being B against a total length of 4. So I actually go ahead and write that out, right? So we have 1 letter, B, divided by 4 letters in bin. And we have the same concept here, right? We have 2 letters, BE, divided by 4 letters in bin. Okay. So what I would want is a way that I could maybe check, there's a no here, but there's a yes up here, so I can work 1 step back. But it's a little tricky because, well, we don't really have a method that could help us do that. And we only have 2 lines, and per the Java syntax, I can't just put a whole bunch of lines all stacked together. So maybe there's a different way to do it. And I think this is the big insight, which is that we're actually going to count the number of yeses. And I think what makes this insight more apparent is when you look at what we had identified as possible things that we could do. Well, we can find num keys with prefix. If we compare if we use the prefix as the letter B, well, we know the num keys. The num keys is 1, 2, 3, and 4. In other words, we have 4 letters across 4 words. So I could actually break it down as 0.25 on every single level. So let me go ahead and break that down and make it more clear what I'm talking about. I'll talk about what exactly I mean in just a moment. So I have 0.25 here, and the difference is now I can assign this as another 0.25 and here as another 0.25. And then finally, this Beanie Boy has 0.25. And then I can come down here, create another 0.25, and finally, I create Beanie Boy 0.25. So if I'm to sum up all of these 0.25s, well, it turns out I get the same value, right? If you look by word, now it's just Beanie Boy has 0.25 split across 4 things. And each time what we're doing is we're adding an extra letter, and we're trying to see how many matches we have. We don't really care about what exactly the match is. And that makes our life so much easier because now we don't need to track, well, is belt no in this case? Was it yes in the previous one? Well, if so, then let's give it a higher value. Instead, what we do is we break it apart by looking at every letter and the weightage of every letter. And this is pretty important. I'm going to write it down. The weightage of every letter is determined by this very concept here, where we take 1 and we divide it by the number of things in the length. So we have that. And I think that's really the key insight that really just breaks open this question. And I want to reiterate that the way you come to this is by looking at what strategies you have available to you. We have contains. Well, contains is not really going to help us because, well, the prefix that we're looking for might be contained, might not be, but also more importantly, the key that we're using might not be contained. So it's really difficult to determine that. And then we want to do num keys with prefix, the longest prefix of, well, num keys with prefix fits in pretty well here, right? Because I know that if I'm using the prefix as B, the letter B, I know there's 4 things. Longest prefix of also doesn't really help me because it's not like it's very easy to delete a word. Like I can't just find the longest prefix of, delete the word, then do the next longest prefix, etc. We don't really have a great method to do that. So I'm left with num keys with prefix and some way to do it. And after some deep thought about this, I've come to this final conclusion that I need to do it this way, where I break it down letter by letter and proceed forward. So I have this sort of figured out, and now I'm thinking about the exact implementation. So I think now what I'm going to do is sort of start writing in some stuff. It might be possible to do this on 1 line, but I'm going to go ahead and break it into 2. So I have 1 line that's going to do something, I have another line that's going to do something. Well, what if we use num keys with prefix to find the number of matches? So if I'm to call num keys with prefix over here, well, I get 4. And if I'm to find the total sum, right? After all, what we care about is the similarity sum. Well, this just sums to 1. That's the same thing as doing num keys with prefix if I call it with the letter B and I divide by 4 because there's 4 letters in bin. And if I do num keys with prefix over here, well, if I look at the number of keys with prefix BE, that's 3. And 3 divided by 4, right? Because we're weighting it divided by the letters in B, E, N. Well, that's the same thing as adding 0.25 3 times. So I think that's where we're going to use num keys with the prefix. So actually what I can do is I can break this apart into 2 steps. The first is I want to find the matches at every level. So what I'm going to do is I'm going to use num keys with prefix, and to sort of demonstrate how we're going to build up what we're checking by this comparison, we're going to do key and we're going to use that dot substring method. And we're going to go ahead and go from 0 up to index. This way, we're checking 0 to 1, then we check 0 to 2, right? Then we check 0 to 3, then we check 0 to 4. And that 4 will break because we have that base case that's going to tell us, hey, you're at the key length, make sure you don't go one more. Well, you're going to go 0, 5, but you're never going to get there because as soon as the index finishes with 4 and then you hit 5, you'll hit the base case and then you return that 0. Okay. We might have to come back and change that 0, but let's see if we will. So now you have matches. So now what we've done is we found this. Num keys with the prefix, we found that output. And now we need to divide by the letters in B, E, E, N. Let's go ahead and do that. So we get matches. And then, well, how do we find how many letters there are? Well, same thing we did up here. We're going to do key.length. Okay, well, it's giving us an error. Why is it giving us an error? Well, the reason why is that matches is an integer. Num keys as a prefix gives us an integer, right? Because it can only be an integer number of words. We can't have 0.5 of a word. But we need to cast it to a double. The reason why is that we want this to be the aggregate decimal score. So we're going to go ahead and cast it to a double, so that way it converts, the integer over integer division doesn't truncate. And then we have matches divided by key length. But hold on. There's one little part that we're missing. One little part. Where is the recursive call? Exactly. So we need to increment this somehow. And it turns out, just by doing another check, we were adding everything, right? So we can go ahead and add. And then I can create another call to SimilaritySum, and to mimic the same process of increasing the index by 1, I can call it again on key, and then I can do index plus 1. Oh, I misspelled index. But we can do it on index plus 1. So what this code now does is it looks to check the similarity sum on this, and then we divide by the size overall, right? That gives us the number of words present. And then what we're doing is we're computing the similarity sum by using this little bit of a interesting algorithm here, where we don't really care about what the longest thing is, but we just go letter by letter in the key, because that's something we can iterate over quite easily using the substring. And then we figure out the number of matches, then we divide by the letters in bin to figure out the weightage, if you will, that we give. Okay, well, that looks pretty interesting. And I think that this example really shows how useful it is to try and work through what you're doing by hand and see if you have the space to do it, if you have the capacity to do it. And now that we've done the recursive solution, I think we can go ahead and just do the iterative solution in case you were wondering. It's pretty similar, except there's a couple parts that are a little different. So with iterative solutions, similar to how you're going to have an if for the base case, well, now we want a tracker variable. You'll see this very often. Sometimes you'll call it count. In this particular case, I'm just going to go ahead and call it score. So let's say I call this double score equals 0. Well, I don't need to declare 0.0, right? Because we're declaring it of type double. But now I have for int index, and then we're going to do a very, very similar thing. In fact, I can almost basically sort of just copy this line into here. And then I can sort of say, instead of returning this plus the similarity sum, well, the iterative counterpart to that would be to call like this. And then this is taken care of because instead of summing again, what we're doing is we're adding to the score, right? Which keeps adding to itself because we've declared it outside the scope of the for loop. And then the actual index plus 1 part is being taken care of the for loop itself. So we're going to go ahead and treat this like where we want our index 1 to start, which if you notice corresponds very well with the initial call that we made to the helper function. Then we're going to be treating this middle thing like sort of our base case, right? Except inverted. So our base case is when we want to break. This is like our not base case, right? This is how long you want to keep going. Well, if you want to break when index is greater than key.length, you want to keep going while index is key.length or less. And then what are you doing at every turn? Well, you're adding 1. So we're going to go ahead and do that, just like I mentioned. So I'll go ahead and do index plus equals 1. And then finally, very similar to how you return similarity sum divided by size. I'm going to go ahead and do the score divided by size. And one thing I want to mention is this dividing by size might seem weird to you, but it's totally fine if we are to added in here. It's just that would just make the code even more cluttered and more difficult for us to figure out. So it's just easier to have it on the outside. That was a long question, but I think that there's a couple big takeaways here. The very first one is that the information given to you in the problem is really, really, really important. If there's methods that are given to you and it's said that you may call any of those methods, think about how you can use them, even if the solution isn't really the most clear or straightforward. Like I said, the first thing that came to my mind was thinking about doing it in this particular process where you compare the key to every word of the try. But I realized that because we're not given a clean way, right, a nice way to figure out what the words in the try is, or what the words in the try are, that way becomes a little complicated. And the issue is complications are hard to deal with when you don't have the space to account for them in your skeleton code. So because we were given these specific methods, I thought about which ones I could use, which ones I couldn't use, put some question marks. I couldn't figure out a way to use longest prefix of because there wasn't an easy way to remove words. So I would only get one thing and it wasn't really that helpful. But I decided to figure out a way using num keys with prefix. And that only came because I was trying out the example that was given here and then seeing how I could break it apart to make it easier on me. So that way I wouldn't have to check back and forth.